We can go anywhere you want, okay? I'm happy to chat and talk about some of the stuff. I have slides, another 70 slides from, so last week we went through some stuff. We can talk more about some of the principles. Happy to do that. We didn't really touch on color. We can talk about color. I forget what people, I just turn those down. You need them on? Okay. We can talk about color, we can talk about other principles and all that stuff. Alternatively, and I'm very happy to go here, is I have 7 questions for you, one of which is easy, okay? And the rest of them go progressively more involved, but they're all data related, and we can just actually go through and actually, you can make plots, okay? And again, not with your computer. I'm not going to give you the data. Okay, parse that again. Just to recap what we were talking about last time, and the more and more I think about this, the more and more I'm adamant that it's important, is think before you plot. Just put the computer away and figure out what you're going to plot. Now, this gets you into trouble because the plot that you actually consider may not work. Because of the data. If everything's a big mess, so it's an iterative process. So I'm hoping that you guys want to actually do some hands-on plot composition today. I'm not reading whether that's a good thing or a bad thing yet. But one of the really good tricks, and it's the same thing when I program and write code, is I think of 2 or 3 ways to do something before I do anything. I pick which one is going to be fastest or best in the long run or whatever it is, and then I go. But I know I like to have something, I like to have a backup plan. And likewise with plots, you might want to think, I could do it this way, or I could do it this way. Let's think what I should do first. Again, I'll make the analogy all the time with plotting is the same as writing. You're trying to convey a message. You better have got the message in your head first. And again, that's complicated because you look at the data first to get the message. But it's a different stage. That's exploratory data analysis. Now we're going to actually plot the data to present to others to convince people of the message and draw their attention to the points we want them to focus on. You better have identified that. You better have thought about your audience, what your message is, in what way you're using this. Is this evidentiary, or is it actually sort of exploratory or so forth? Okay, who the audience is and what they're likely to understand. And then you've got this hideous problem of, are they on their cell phone, or are they on an overhead projector? Are they on a website? Can you use interactivity and so forth? Craft the plot to emphasize the features you want the viewer to see. Do not, and I see this all the time, is here's a plot, there's the data, they speak for themselves, everyone can see exactly what I see. No, they can't. You better draw the attention, your attention to the things you want them to extract or walk away with. That can be a caption, but you should be able to do it better. Well, you use a caption, but you should be able to do it better by actual graphical elements. A lot of times just adding a line or a smooth curve or so forth will actually help to emphasize that's the point I'm trying to make. And we tend to just draw plots with raw data and not add these annotations. Very simple principle. If you want people to compare things, if that's the take-home message, this is bigger than this, okay? Put them side by side, okay? If they're on different parts, and this applies to when we actually build multi-panel plots. If you have things that are very far apart, there's a huge cognitive overload that people don't naturally think to compare things that are far apart because, again, you're focused on the wrong thing. This comes down to sometimes you want to reorder the bars in a bar plot. No bar plots. Okay. In a dot chart, you want to reorder the levels in a dot chart so that you're comparing the right things. You don't want to just alphabetize them and have sort of a random array of values. Okay, and if you have these multi-panel plots, you want to arrange them so that they actually in the most natural ordering for the point you want to make. And we talked about this the last time near the end, but kind of throughout the whole thing. We use cues or attributes of a plot, like color and length and an area and all these different things. We only have a few of them because of the medium that we're in. But you want to pick the best cues for the most important attributes and then go down this. And what we mean by best is not the nicest, not the funnest, okay, not the fastest to decode, but the most accurate to decode. And what we said last time was people can, this is going from most accurate to least accurate. People are very good, relatively speaking, okay? They're much better at judging heights or lengths. They're much better at judging lengths that are perpendicular or horizontal. On a slope, they get less good. Okay, so this is a length, but these are harder to decode accurately than this. Okay, so choose heights or lengths, okay, that are perpendicular to the or horizontal. Okay. Length. This, people are pretty good at this, but this is not as good as this because we're starting from a different baseline. Okay, so without the same baseline, that means these stacked bar plots are not good because the second level of this on each bar is starting at a different point, and it's hard to tell. If you're, again, these are results we have from experiments and also from sort of cognitive theory, okay, as well. They're not hard and fast rules, as we were just talking about before. You have constraints. You just can't obey these rules and not use them because one's worse than the other. It's just you want to choose which one you use for what particular effect you're trying to illustrate. So slopes we're not as good as. Okay, angles, slopes are very similar. They're related, but not quite the same. We're not good at area. Okay, but we're better at it than volume, which kind of makes sense. There's an extra dimension in here. Okay, color hue, we're not good at color hue. Okay, but and color intensity. So these ones we can actually separate. But if you pick the right colors, you can do better than picking the wrong colors. So you really want to sort of, these are for categorical separation, but it's hard to tell. And by the way, what I'm looking at on my computer and what you're looking at here are not the same. Okay, and yet they are, but they're not. So these are the cues you want to actually take. And this is the principle that I like to go back to all the time, is this is why length is best. A one unit increase in length will be perceived as a 1 unit increase in value, whereas for everything else, it's just not linear. Okay, so that's the concept, that's the principle. Yeah.
When you were starting off, you said perhaps we could talk about color and then also maybe the 7 questions you have. I am interested in color, mostly because I think that it can be, if you do it right, really visually appealing and draw someone's eye to your figure and make them want to look at it. Because I'm not saying black and white is bad, but I think that if it's creative and artistically done, it can make someone interested in your topic. And so I was wondering if we could talk about color as like an augmented aspect of a career or whatever you had in mind about color.
What's anyone's thought about what you're saying?
My impression is that we can use color to draw attention, but when it comes to conveying a message, it may be more difficult to do that with color.
Sure, yeah, I totally agree with that.
So, but you were talking about drawing people, making it more appealing,
yeah.
and that's a perfectly reasonable criterion to have. Okay, and to draw people in, and this is a problem. This is, we have all these things like infographics, which are intended to do that, to actually draw people in and make them cute in some regards, or relatable in some regards. What we're talking about here is much less that. This is.
Sure, I understand the distinction between
Yeah.
accuracy and conveying data versus appeal.
Yeah.
But I think that appeal is important because we're inundated with data and information, and I think if we can make it appealing for your reader, they're more likely to spend the extra time to understand what it is you're trying to convey, your lengths and heights.
Yeah, no, I definitely agree. Now the question is, so where do you use this?
Exactly.
I mean, do you use it in the actual values? Are you encoding an attribute with the color, or are you just actually decorating the overall plot? And that's a very artistic sort of a design-oriented thing, which I'm not particularly. I'm neither. But it's a very now you really have a different audience and a different purpose for the color, and that's fine. So you're about to say?
I was going to say the chart you have up is, I think, a good example, because if you made that black and white, you'd still be able to read it.
Yep.
So you're not encoding anything with the color, and yet you've illustrated it with color.
Thank you. Yeah, I mean, there's no doubt about it that you can liven things up. I mean, I come from a particular world, which is you let the data speak for themselves, and it's scientific, if you will. And that's I'm on the STEM side in some regards, and so what's the purpose? So we tend to think, oh, you're not supposed to actually try to make it more appealing, and also it's in the context of a paper where somebody has chosen to read the paper. So this is slightly foreign to me in some regard, but I know exactly where you're going. I personally think color is the least interesting thing to draw somebody in these days. I think it's interactivity.
Right, but again,
Exactly, and this is why this is so darn hard, because you have to tell me who your audience. So what we're debating here is who's your audience. In my world, I have a referee for a paper, or I'm reading your thesis, and I'm going, I have to read it. I don't have a choice, and I'm going to look at your plot, and I'm going to hope your plot saves me reading 2 pages. So, whereas if you're, as you say, inundated with material, why would I look at this? And now, if the plot is the entry point, then it better be very engaging, and it may be the entry point and end point, in which case then they're going to have to take everything out of this plot. That is asking a huge amount for a plot. It is really seriously hard, and I think it's easier with some interactivity, more specifically animation. So you got all these different criteria. We can talk about it. As we go through, we'll talk a little bit, but it's seriously hard. I mean, but again, what I'm trying to get at here is, you have to identify what your criteria are for evaluating how good it is. In your case, you're saying it's appealing. The goal is to get people in. And then it's got to do a double job later on. So then you need to know who the audience is. You need to know what the purpose of this plot actually is, which is now it's just to get them in the door, and they'll read the caption later on, potentially. Just thinking about all of these things makes your plot better, in my mind, or at least it allows you to consider what trade-offs you're making. Okay, I'll try to weave that in. It's a hard one though. Okay, and we can talk about color. I mean, we like it's the reason is, and so it's a very good question. And one that I'd like to be able to answer better, but it's so much easier to tell you how color works and how the cones and rods in your eyes work and how you do, because that's just scientific. This is fuzzy, but it's not. I mean, and there are good design principles behind all this stuff. So we can talk a little bit. By the way, I meant to show you this last week, but I couldn't find it in my slides. This to me is one of the best pie charts I've ever seen in my life in terms of, wow, that's really stupid. Pie charts, we said, were not good. But this one takes it to a whole extra level. To actually put it on to have it at an angle. And so I say, the reason we don't like pie charts is because of the angles, because we're not good. That was third on our list of ways to decode. How good we are at decoding the cues. So, but this distorts the angles in all sorts of interesting ways. So that's kind of an entertaining one. Okay, so that was my first bad plot. Kind of, again, we did this last week, which is let's look at and evaluate some plots. Is this a good or bad plot? This was a bad plot. Is this a good plot? Why? So if you're going to say, so you got a 50-50 chance, yes or no. Now you got to say why.
Well, back to color, I feel like it's drawing your attention to the background. I mean, because that's the part that's in color.
Which color? The red one? Yeah.
Like,
You're saying that it calls your attention to that.
yeah.
And it does, and it's right. It's doing exactly the right thing.
Yeah, axis highlighted.
It what?
Sorry, the axis is blue.
Yeah.
You're used to 0 at the bottoms.
So it's a beautiful plot. It's intentionally bad. I'm misleading. Okay, but the fact is, it does pull you to the right thing by accident. But this is intentionally just screwing with the axis to make a very important political point. Okay, that's incorrect. Okay, and
There's, I don't know, the X is the without scale.
That's the least of our worries. Yeah, I mean, I think they're actually okay. I mean, in terms of the gaps between them are still consistent. But this is one of those wacky things. It's actually pulling you. I mean, and again, it's humans. We just know what's there. We don't actually. When you're reading, we often just read, and we know we fill in the gaps. We fill in words, okay. And sometimes we're wrong. This one we just fill it in because that's the curve. You see it. The curve is it's upside down, and there, okay. And they're pulling you in and taking advantage of conventions, and it's kind of wacky.
Even after you said it, I didn't see it.
It's hard. It's like, who on earth counts this way? Actually, I do a lot. just this morning, I was counting down because when you're drawing in PDF documents, the top left corner is the origin, and you go down. So there's reasons for it, but everyone's conditioned to go this way. So again, just thinking, but it's funny. It's exactly right. It's like the color's wrong, but no, it's technically right, but exactly the opposite of what we expect. Jane pointed this out to me yesterday. She was saying, "Here's an example of all these plots." Does anyone know what these plots are called? Has anyone seen these before? Okay.
Sports. Sports.
So they're I call them radar plots. They've been called radar plots for a while because you kind of think of them as being this is on a particular shape, but often they're circular. Okay, is this a good plot or a bad plot? So here's a new different plot type, that you may or may not have seen. What's it representing? So let's decode this one a little bit. And again, so one of the ways to evaluate if this plot is good is, can you extract the information? Can you decode? Can you compare things? So it turns out, now let me help you look at this. It turns out, so what do each of these points mean? Does anyone know how to? So you've actually got labels here that says this is party loyalists, Hispanic and Asian, black voters, millennials, the left. Okay, so these are sort of types of people to whom these candidates appeal, would-be candidates, okay? And somehow this says, we're assuming, and again, well, it does actually say, small is least, okay, big, further away from the center is most, okay? So this is length. We are dealing with length here. That's good, okay? Although there's area. So what are we looking at? Which cue are we using? We're looking at direction for one, because you got and we're looking at length. The area is actually not particularly important. It may be misleading, but that's another matter. Okay. I mean, you could compare them by area, but it's not clear that you would be using.
How balanced is that, right? So it's like how much adherence to that direction, that point. It has some, it conveys some meaning actually, because but we use this a lot in neuroscience. Okay. Because you want to show like a particular cell, which direction is steering to most, right? So it could be tuned anywhere, any orientation. Okay,
we'll come back to that in a second. Okay, so can you be in? Well, that's good. Can you be in any orientation? What does this value mean here? Okay. So, but it is a length. So it's kind of weird. You're connecting dots, but these are actually categorical values. There's only 5 categories, and you can sort of see how this. It's not actually even clear that. It's not clear to me that you can't. I think somebody could be a millennial and Hispanic. Just thinking. Okay. So these aren't even actually, these are overlapping categories. So this is kind of a little odd, but that's okay. That's fine. Okay. But so you've got length essentially. The area doesn't mean anything here. Okay. It may be misleading. And so, okay, tell me this. Who has the greatest support from the party loyalists? That's probably that's not party loyalist. But this touches the edge, but it's not party loyalist. Sorry, I have to go up to the label over here and say it's over here. It's Hispanic, so not that. I was just looking. So the comparisons here are a little far away because you actually have to compare these guys to this guy. Anyone? So is this working or not? What's a better way to do it? Now you got to go compose a plot. How are you going to do it?
Compare each category.
How?
Just side by side, everybody side by side, like bar chart.
I'll give you one more chance. One more chance. What? Instead of a bar chart, what do we use? Yeah. Yes. No, we will just use this. A lollipop plot will actually get in the way here, okay? Because what we probably want to do is maybe something that looks like this. So let's put down loyalists. Okay, and now what we can actually do is we can sort of put something like this, and another person here. So this is, who's this? This is Amy. Okay, so that would be Amy, and then we'd have, and then Joe Biden would be here. You know, we put this down here. We can use different glyphs if we want. That's what I'm doing here. Okay, so we could actually do this. And now, if I do a lollipop plot, the lines are gonna intrude, if you will. Of course, I mean, I could do it this way too. I could just do it by Biden, Amy, and I could do this. Okay, so I could do this, and I could do this, and I could do this. Okay, so which are we going to do? So I've just drawn two.
What you want to put all your theories together, maybe it's better in the first one.
It's in the first one. Thank you. Sorry. Okay. Yeah, because then what I could actually do is I could put down Hispanic here, and I could do it this way. Of course, I can flip the axis too, because now we're counting, so we should be counting on the horizontal axis. So I can flip my dot chart around, but I can actually now. So hopefully, what I'm going to see, and if I did something that looks like this, we'll do this, and we'll do something like this, and we'll do this, let's say, and then when we get over to the millennials, and I'm just choosing the order here because I've run out of space. And that's not a good thing. I should order them based on maximizing what I'm trying to show, the effect that I'm trying to.
The problem with this is that you have so many, like 10 candidates there, right?
Yep.
So you would have in one line 10 dots, and then I have to remember which color is that, like 10 colors.
I've only got one color, it's red. So I could use colors.
I agree with it though, because to me the graphic is more about overall who's probably the best candidate for president right now. And you can see really quickly who has, like, I know you said it's not about area, but Kamala Harris probably is the most appeal among all of the groups. Where you can't get that if you're looking, you'd have to go, okay, well, they're high on millennials, but high on millennials, high on Hispanics. And then you can see much more easily in each separate.
Over here?
Yeah, over
So-
there.
So,
But overall,
Adam?
You could connect the lines though between my fellow taxis and dots, all this.
So we go down here, and then let's put this one up here. Okay, so what we can do is now we put in a subtly chosen line, so it doesn't actually, so it helps draw your eye to the connections. Okay, so now you actually sort of are seeing something like this, and you might find that, you know, Kamala Harris is right in the middle of everything, or whatever it is. You will potentially see this.
I think to that point, that might be what they're trying to convey, but that's not what the data. Yeah. Right? The data doesn't say that because she has a bigger area, she's more likely to appeal to those groups because there's a different number of people in those groups.
Yep. This is hard. But I mean, just drawing these and sort of saying, which one should I use? I mean, the very simple point is just mapping it. It's very easy to do this, by the way, in a piece of software. You just plot it and go. But then again, before you do that, because human nature in my experience is, I make a plot and I walk away. That's fine. First of all, it's just like you say, plot this. I don't have no idea what's going to come up. There it is. It's not so bad. I walk away. Okay. Other people will sort of say, I need to actually try to make this appealing to engage people. That's a whole different ballgame. That's fine. But if you already know that there's two possibilities, If the software allows you to make them quickly, make them both and then think. Think hard about actually which one is conveying and if you can move them around the place. Yeah.
Are there too many dimensions here for using just a 2D static image for conveying this message?
I don't think so. I don't know. So what we're actually doing over here, the answer is maybe, but this is where it's probably a good idea depending on, I mean, if this is something for your own purposes and you just want to see something, you just look at it and go, I got what I want. If you're doing exploratory data analysis, this might be just fine, and you puzzle over this. And again, we're not going for quick understanding of what's in the plot. We're going for good understanding, like accurate understanding. So sometimes, you know, one of the plots I showed you last week had 2,222 observations in it. That should take you a long time to actually decode, okay, as opposed to, sure, I look at it, this is taking me more than 10 seconds to understand. Well, of course it should, okay, so it's not speed you're going for. But if it works for you for your purposes, that's great. But when you think about handing it to someone else, maybe it's too much for them. Then it's good to actually talk to your collaborators or your peers and say, hey, what do you see when you look at this? Oh, okay, fair enough. That wasn't what I was going for. What we're doing here, but does anyone know what this kind of plot is called? It's a dot chart it's a dot chart. Remember, I told you dot chart is a scatter plot, and it's the scatter plot. And what we actually call these things in some regards, this is a parallel coordinates plot in some regards, okay? When you go from 1 dimension to 2 dimensions to 3 dimensions to, oh dear, okay, we've got 4 dimensions. One way is just to say, here are the dimensions, and now we just connect the observations that across their dimensions. And that's what I'm doing here. We've got all these observations, here are the different dimensions. As you get more and more of these, you get less and less space, so they're closer together, which is good. As you get more and more observations, you get spaghetti. You just get this big whole thing. I'm hoping that because we've only got 10 people here, this will work. So that's why I'm saying I don't think it's quite. The number of dimensions is not so bad. That's okay, because I say they get closer together. It's when the number of observations.
Number of noodles.
The number of long noodles, yes. The number of noodles gets ugly. And it also depends on, and this is likewise with a pie chart, it depends on the values, not just the structure, but the values, which are, if you have this, which is all the X's are at the top, so Joe Biden's all at the top and Amy's at all at the bottom, it's easy to see that parallel, and you're seeing very similar features, like, oh, this person is uniformly lower in all scores. If they start crisscrossing, it becomes a little trickier, but that's part of the data you want to see, and that can actually be fine. This is what we actually do. We do use these in parallel coordinates plots for high dimensional data when you run out of things. The ordering again is critical, because you're comparing. Oh, look, these guys go. They all go down. Okay, between these 2 variables, and they all go back up again for the 3rd variable. If you get the order wrong, you lose that locality. So yeah, to me, this is probably not a really good plot. But you mentioned something where that makes them a good plot. I don't know that I have an example. There's a woman called Florence Nightingale. Anyone heard of Florence Nightingale? Hopefully. Okay, I'm never sure if this is a cultural thing. So I grew up in Ireland and close to Britain and that sort of stuff. So it's more of a British thing. But Florence Nightingale, back in whatever it was in 1700s, actually invented a particular type of plot. And it's kind of useful. I'm not sure how useful it was. I still think it's probably not a good plot. But then if you extend it, so to what you were saying, which is you have an orientation that can be absolutely anything. Well, and then when you draw it, well, this orientation, which is 1 degree, is really, really close to 359 degrees. If you're just going to wrap around. So here there's an orientation that says these 2 things should be close together, and I want to measure the distance from this. So if I did something that looks like this, which is Here's 0 degrees, 1 degree, 360 degrees, and I see something that looks like this. Okay, these are back at the same point, and I can't compare them. Okay, whereas if I do something that looks like this, and I sort of see, what am I doing? It's so it's very small here, and then we go over here, and we go over here. It's getting bigger and bigger and bigger and big.
Small, small.
And then it gets small again, and we see this. You can kind of pick that up.
If I want to change this, just modify the bit. Instead of area, I would have put a dot in the center, and then put arrows in 5 directions based on it.
And that's what this. And that's what this is. This is called, I call this a Florence Nightingale plot. It's a windrose plot. You've actually got an orientation where they use these for wind. Where this is, I think where they came from, where people are measuring the wind in different directions, so that the velocity of the wind. So you actually have this, and you can discretize them. What Florence Nightingale did was this. I can pull up a picture if you want, but what she did was something that looks like this. And they went up there, and they went over here, and then it turns out that you're down over here, and there's basically zeros here. So this is the same as this, except for it's not. What's the difference? This corresponds to an actual orientation. What Florence Nightingale was doing, this is January, this is February, March, so there is a connection. So January and December are close together in some regards. Maybe there's a seasonality here. So that was kind of what drew her. But what's going on here? It's back to area again. You're back into the pie chart world, which is not good because we can't quite figure out. So here we're back. We want to get back to the Q, which is length. Okay, and this is what we're getting at here, which is exactly what you're saying here, which is just draw a line here up to the thing, and then you may have this. Is that effective? No, because we can't see. We can't say that this is half as big as this. Okay, this one we're almost able to do. Wait, let's think about the Q's for a moment. This is about, if you put the center in here, this is about half the distance of this. I don't know what you're seeing. Okay, one of the reasons it's hard to see is because what we're actually doing is this. We're basically saying it's this distance to here, and then there's it's taken from this point. So they're starting at different baselines. They're upside down. We're going up in this direction, down in this one, and trying to think. And this is easy. This is easy because it's vertical. When I'm trying to compare it to this one over here, I'm on a slope here, so this is not good. And again, so go back to, well, let's just lift this one up, and it's over here, and we count it from here, and we're back to our usual length, which brings us to this plot over here. Okay, or this plot here actually. Where we're stacking them up on top, and now we've got a choice. It's, the annoying part is, just draw a scatter plot. 99% of all plots are scatter plots. There's a reason. It's because they work, because you're dealing with lengths and all. So there's nothing new here, but what I'm hoping is there's a why. You mean that you actually, and you can think about it and go through these different things.
So I looked this up, so I was curious. And Nate's goal was to show that
Nate Silver, by the way. This is a plot by Nate.
Candidates should have a majority from 3 out of the 5 groups. So I'm not sure that this works with his goal either, which is to show that they should be good. They should have a deal in 3 out of 5 of those.
So if that's the goal, how would you make the plot? You want to rank the candidates based on and show that they have that they're closest to having the majority in 3 out of 5.
You do the dot plot you have more on the right, where you're grouped by candidate, not by grouping.
Okay.
And then if you're talking about the majority, you could just put a dashed horizontal line across it that you can see are there 3 of their dots above that line. Is
that going to work? Does the majority work the same way? for all
Yeah,
candidates.
I don't know if it's majority.
Yeah, I'm not sure you can.
Is comparable?
So I mean, I think if you either way. By the way, these, as far as I can tell, I'm not. I'm thinking this. I'm not thinking about this very carefully. These plots, these two plots, are essentially the same. They're just flipped. And again, we talked about this last week, which is everyone draws them this way, and you look vertically and you measure vertically, and yet we typically draw things along a horizontal axis. So it's kind of a weird human conditioning that we draw vertically. But they're essentially encoding the same information. But that doesn't mean we decode them the same way as effectively, but either one works pretty well. I mean, I think you're basically, I mean, what you want, and this to me is where you would then go and change the order. If your goal here is to look and find out, you just plot them and see what's going on, and you have to do arithmetic in your head to see who's got 3, who's leading in 3, okay? And then you go back and say, okay, let's flip them all around so it's clear that they're going from best to worst or worst to best, depending on your point of view, okay? And so what you're trying to see, and then I think this will expose it, which is you'll see that you get the X, this go down here, and then the X and the X and the X here. So these are, they're not winning because they're relative to other people. And so I think the majority means that they just have, it's relative to the other 9 candidates. You have to beat them, which is, there's no absolute line. So you have to do this across all, where the other lines are, which is tricky. But yeah, this plot doesn't work. Another thing you can do is, actually, this loses information. Another thing to do is actually count who is the winner for each of the 5 categories, and you count the number of times that candidate won in each of the 5 categories, and then you just plot that. And anyone above 3 is a winner. Okay, is an eligible candidate. So you've lost all the 5. You've lost the 5 values, but you're now actually pointing to what you want. So who'd like that? Well, you now would basically just say, so I think what I'm trying to say here is, here's Biden, blah, 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 all your candidates, okay? And here is number of categories you are highest in. Okay, now, and then you draw this is 3, and anyone above 3 wins. So this person, and the other person, okay? And that answers your question really fast. But you've lost all of the comparisons between the things. So this person won, but was very, very, very close. They were only like 1% difference in all 4 categories, or all 5 categories, but they won. So they got a 5, but there's another candidate who came second. So this doesn't quite get there. This is hard. Yep.
Would it be too complicated to use fill versus blank glyphs? So if you had your 10 candidates and your 5 categories, and you have circle, square, triangle, and if you have a filled circle, then you're the leader, and an open, then you're not.
You could definitely do that. Of course, the height tells you who's winning. I mean, the height tells you that you've won because you're above everybody. Yeah. So I mean, there's different ways to do this, but this plot doesn't really get you there. But this is hard. And again, we have to figure out what the message is. And Kristen looked up what Nate's message is, which that's an awful lot of screen real estate for something you can say in a sentence. And that's the problem. At the end of the day, the plot is redundant. You can just say what the message is in English. So this becomes an evidentiary thing. I mean, it just justifies the conclusion. It's got a very different purpose. Okay, but it's not even clear that that's the case, that it's working here.
I think that what you just said tells all the story. The things that what message are we trying to convey? Because at first when I look at that, and I looked at it, say, okay, well, what's the spectrum of voters for each candidate? So then we change the question, and then we start looking, which one will win, which is the best, but which message do you want to portray this?
Again, and if you're doing it, if it's exploratory data analysis, you want to try a couple of things to see where you're trying to find the message, and then when you're actually trying to present the message to somebody else, it's a different mode. Yep, and and I'm saying it's hard. I'm not trying to. You can critique any plot. any plot. But one of the reasons I wanted to look at these, there's a whole lot of new plot types. A lot of them can go back to the dot chart and scatter plots and so forth, and it's not clear that we're gaining much from them. But this one does introduce the fact that it gets us to the wind plots, the windrows plots, which is if you have orientation data where and 0 and 360 degrees are the same thing, they should cycle back, or else it can be hard to view. So it introduces that, yeah, circularity is good. This is the one we sort of said it would look like this, and I said we could have a windrows plot. What's the drawback to this? What's the drawback to this approach? Axie?
You don't, like with the length, it's better, it's all of the same.
Because now we're comparing slopes. So is this one twice as big as this one? We're at non-perpendicular lengths, so it's a little hard to. That's one thing, but you still get the picture. Although it's easier to get the picture here in some regards. The problem with this is we don't see the wraparound, so we have to go all the way over. This is the principle I was saying, put things you want to compare locally, but hang on a second, you just can't do that. You can't have everything right beside each other for the purposes that you want. So you got to pick, it's just like writing a paragraph, you got to pick what your main point is, even though there's 2 points, okay? But here's another problem with this. So this is the wind, this is the wind in the delta, okay, at the base of the delta, okay, the Carquinez Bridge, and this is the wind down in the Golden Gate Bridge. We'll keep to the bridges. I'm in a good mood with bridges these days. Okay, so here, you see this sort of thing. It's very hard to compare these now. Whereas if I did this, I might sort of see a different effect. And again, we're stacking them. So again, what's my purpose here? If I put these on a map, then I want to actually anchor them close to where they are so there's meaning. Then this becomes a secondary issue, if you want. It's a lookup issue. I'm not trying to compare. If I'm trying to compare, I'm over here. I wish there were principles that you could just say, here's the way to make any plot, but it doesn't work, okay? But so there are trade-offs. Yep.
I guess I have an idea for your next workshop. It's predict who's gonna win.
Oh. I don't care who wins. I only care who loses.
It's in sports. Everybody uses this kind of like the chart you showed before.
Yep.
In like football and basketball, everybody uses this chart. And it's no.
They do. People use plots all over the place. And again, they use them to draw people in, as you say, and then they're attractive. They're not necessarily meaningful, but they're part of window dressing. That's why it's much easier to talk about sort of academic plots where there's a goal, and the goal is to be faithful to your data and actually make the. Whereas these other ones are exciting. Remember also the medium that they have there in sport is typically animated, interactive, so you've got a whole different world. But again, the purpose is slightly different. But they're using these all over the place. What's wrong with this plot? I'll tell you, there's a problem with this plot. This is building size. This is a house. This is housing data from San Francisco. This is price, I think, for and there's a relationship here. The bigger the house, the more expensive it is, but it depends on the neighborhood. There's all sorts of other things we'll get to. Okay, but what's wrong with this plot? And how are you going to fix it? Log it. I'm not. That doesn't bother me so much in the sense that we could definitely take the log of this because it's kind of nutty. It's because it's at the Bay Area, so it goes from a ridiculous amount to an even more ridiculous amount for a house. Okay. So that's fine. But so we could definitely take logs, but we're not seeing a massive where we see all the points are clustered over here, and we have these massive outliers. It's somewhat well spread out. There's not big gaps. But definitely take logs if you want. Are they?
You want a density.
There's an awful lot of there's an awful lot of overplotting, but you can't tell how much. You just know we could actually be very, very lucky to actually have one point at each of these, and they just happen to all connect and make a nice black thing. Or we could have, 25 points at each XY coordinate. So that's when we get to something that looks like this, which is a smooth scatter plot, okay, which is easier to see this way and more clearly, which is you actually end up with these little shapes, and then you just color code them, and you've lost information, okay, because there's now multiple points in here. You're not seeing the individual points, but the whole point was to show the trend of the relationship, not to look up individual points, although we can't look up that outlier here individually because we've lost it. Potentially there might be 2 points in there. So you've definitely gone from lookup of individual points to, I'm going to start walking around. Pamela's trying to figure out the new camera. She's having fun, but I'm going to make it hard now. Yeah. So this is, it's a pretty obvious plot to make because there's just an overwhelming and overplotting going on. Why do we use this shape, this honeycomb shape? Because we get full coverage, okay? Because if you put circles down, you'd have gaps, or they'd have to overlap to actually fill it all in. So this is just a tiling operation, okay? So it makes perfect sense, but that's why we pick them. Okay.
Why do you prefer hexagons to squares?
Pardon?
Why do you prefer hexagons to squares?
Yeah. You could definitely use squares if you want. This one sort of there's a notion. There's a notion that you're kind of you're not just going horizontally and vertically, that you are actually sort of mixing a little bit better. That otherwise you are, what am I trying to say? You're just imposing a particular ordering on it. This one gets a little bit more coverage about the correlation, but how much? I don't know. This is, by the way, whenever you say got counts in here, this is a bin width problem again, just like the density and histograms. You have to choose the bin, the size of the bins. You can, let's just have one big bin, okay? And you just say, look, there's n of them on the plot. So obviously you can choose different things, but you could potentially see multimodality. That there's a peak here, a peak here, and a peak here. Then you'd be able to pull that out. Again, what's the goal? This is your parallel coordinate plot that I was talking about earlier. This is 11 variables, 32 observations, bit of a mess, okay? You can move these guys around to actually try to focus in on some of the features, but you are sort of seeing, hey, there seems to be a correlation between the miles per gallon and cylinders, a negative correlation. Okay, low miles per gallon, high number of cylinders, and so forth, and you can see some things. One of my colleagues said, "Has anyone ever seen anything useful in a parallel coordinate plot?" Kind of. Okay, dot charts, yeah, which are parallel coordinates plots, but these can get messy. But what you really want is interactive software that just you can move these guys around and actually see what works well. But you can do that manually in static software. Okay, so then if we want, we can go through data visual. We can go and look at a bunch of plots. Almost all of them turn out to be scatter plots, but with new names. Okay, I'm more than happy to go if that's what we want to do. Somebody was going to, sorry, I heard somebody going to say something? No. So we can chat about. Oh, hang on a second, I lost that. We can chat about. If you want, I'm happy to. We can talk about color. We can talk about different things. We can make these plots if you want. You can go off and play. We'll do it. We can do it together. You can actually sit down and think about it. Do you want to do that? What does anyone want to talk about? I got 7 questions.
Let's do a challenge.
Okay. How do you plot this? This is the easy one. This is just to get you. This is easy. But this is actually a table in a paper. I mentioned this paper that Andrew Gelman and his colleagues wrote about practicing what we preach, which is to turn tables into plots and put the plot rather than the raw data. This is a page of data. There's about 37 observations. Okay, that's nice. So, you know, when you're working on this stuff, it's only 37 observations. You want to put that in your head and say, great, that opens up, that changes how we're going to consider plotting this. Because if there's 37,000 observations, we got to aggregate in a lot. We may be using smooth scatter plots or whatever it is. So how do we plot this? I can't remember. It doesn't really matter, okay? But you know, but the basic. I mean, even from this, I should tell you, but I'm just giving you this. I was putting this together quickly. Okay, you've got the ID of the observation of the subject, 1, 2, 3, up to 37. Okay, and then you've got this is the response. Okay, that's what it is. It's response 0 or 1. You know, if you want to think about it, did they get better? Did they not get better? Okay, this is the dose that you gave them, which is some numeric value ranging. Okay, and then this is the number of days that they actually got this. So this is easy. They're going to get harder.
That's like a survival curve.
Is it? What do you mean by survival curve? Ooh, okay, now we go. Okay, so we have all these terms for things, so, but I bet you it's a scatter plot.
Your groups. I don't know, like the response to the groups, like zero being no response and one being no response, and then, or if it's
so what are we going to put?
under control, I don't know.
Yeah, so what are we going to put here? So I mean, so this is, you know, you want to bring it into context. Survival is a very natural thing to think of here based on the data. You got a dose, you got the number of days, which is kind of different. That's an added component to the survival curve. Normally you sort of think about, I give you this dose, how many people survived or whatever. So we got cumulative effects. So we got to try to think through this. It's easier, of course, if it's your data and you actually know what you're trying to do. I'm coming in cold, to say the least. Okay.
So this versus those.
Okay.
And then the color, I would color black or white, whether it was response was 0 or 1.
Okay, so this is just done. Okay, that's one approach.
Yeah, and it's scattered. We do it scattered.
So we're.
I would know if I increase the days or how those and days is related.
And I'm going to be very literal. You said make it black and white. Okay.
So first.
So there we go.
No.
I can't use white. I can't use white. Okay. So yeah. Okay. So we said, you know. So okay. So we'll.
Yes.
Okay. Okay. So and that's filled in.
So the number of points, so that you have 37, you would have 37 points there.
Now there's 2 points. They overlap, but you can't see that because I'm filling one in, but not filling the other one in. So we actually, how we choose the glyph is a little tricky. What's that? We could jitter them, or we could actually just choose a different glyph. We might actually use that and a plus, and that might get us a little bit better. So choosing the glyphs, depending on if we need to be able to look up the individual plots. So we have a lot of control over this. But again, what do you want people to use? What do you want people to do? But this seems actually like probably the most obvious thing to do. We got days and dose, and we're basically sort of saying, and then this is the response. Yeah, RSP. Okay, as to what it is. So it's a third dimension. So it's 2 dimensions, days and dose. These are actually somewhat numerical variables. This is a categorical variable. So we'll just. So what else could we do? How does this work? Anything? Are there any? Remember I was saying it's a good idea to have 2 or 3 plots in your mind, and then go, okay, that one's the obvious winner, or they may have different effects. Oh, yeah, you're all very quiet now. You're critiquing everyone else's plot, but when you have to make your own.
I might try to do a box and script plot for say days with the response variables compared right next to each other.
So tell me what. So it's a box Whisker plot for days.
Right.
So we're going to see something that looks like this, which is here's your days, and it goes between. This is 1 day, and it goes up to 5 days. So where does the dose come in?
I would maybe make that another category, compare the response groups to one another.
So it's up here on the same plot, because the dose goes up to 24. So if they're on the same plot, we've got 1 to 4, and we've lost the connection between I think so. This may, you know, when we look at this, when we're doing exploratory data analysis, the first thing I'm going to do is summarize each one separately. Okay, so yeah, tell me the box plots for days. Okay, oh my God, there's somebody who's been on this for 365 days. Hang on a second, that's an error. Okay, and then we find out that that was actually 36.5 of the dose, and there was an error in the way the data. So this is cleaning the data, and we're using a plot to do that. But now when we're actually trying to find the relationship, it's a different question. Okay, so we do this. We do univariate EDA, exploratory data analysis, then we do bivariate and multivariate, and now we've only got 3 variables, so it's good. The ID is actually a variable. You may actually want to see, is there a trend over ID number that somebody actually has sorted these, or that there's something in the protocol that's messing this up. But that's another matter. But in this case, not so much. So, but these univariate, the box whisker plots are not getting at the relationship because we've lost the connections between them.
To be clear, I'm saying that you plot these box whisker plots for response equals 0, response equals 1. So
Okay.
it's basically a visual t-test to get kind of an idea.
T-test. Yeah. Go
An idea of the difference between the days or the dosage, right, for these different.
And we'll put these on a different, and we'll put these on. Yeah.
So, but you can use another y-axis on the right, and so you have so you would have 2 y-axes. One would be there, your objection was, oh, your dose is gonna go up there. I'm saying let's move it down. You don't have to put it up there.
Oh, I'm gonna.
If you have a y-axis on your right, that means dose.
I was joking. I wasn't joking. I was being intentionally sort of, tell me exactly what you mean in the plot, that we can't compare these. I knew you weren't going to compare these. But so no, I'm going to move these down by actually making 2 plots. But I'm not going to do this. Wait, this is days and this is dose. I can't do that because they're not on the same axes, and I'm not going to do this and put another axis here because now you don't know which axis refers to which. Okay, that's a real mess. There's a religious rule that says you never have a second axis. And like with all rules, violate it whenever it's appropriate. Okay.
At the beginning of workshop, you gave the example like how they thought it.
I did show you one last week where there was actually 2 things. And remember, I drew it on the board here. It's in my office. It's Howard Wayner's one, where he actually drew this nice plot. I was saying to it, it looks like this. And he drew a line in here and a line in here. And this is the log odds for the smokers versus non-smokers. And he was persuaded. He wasn't persuaded at all. But during a conversation with people as to how to make it a better plot, he ended up with this and this, where this is the non-smokers and this is the smokers, and this is because this guy goes to this axis and this guy goes to that axis. And it's worse than the red mess that I showed you about the gun laws. It's bizarre. So it's all well and good if you do something that looks like this. If you put a line here and says these are 2 separate plots, and there's a visual cue that says that this y-axis for that. I've made a plot like this myself. Not sure I'm proud, but where you actually sort of say this is a different color, and the color corresponds to the thing. But you're playing with fire here to actually as to whether people will misinterpret this. So you can do these, and you do get a visual t-test. Or more to the point, you just get a visual test or comparison, because I never would go back to the t-test. Okay, and of course we don't get the t-test because we don't know how normal these are, and we don't know what the sample size is, and all these sort of things. But people they've come up with this idea a long time ago where you put notches in these, and the notch tells you the variance, essentially the standard deviation or the interquartile range. It's like, okay, and people do. And so what they actually do is, so you'll see in certain cases for a box plot, this is what we get. And it goes up to here, and then you have an outlier here, and you go down to here. And that's what they look like. And then somebody came up with the idea that what you can actually do is you can take that, and you can actually do this. Okay, and for another one, it might look like, so, and this one here, Okay, well, this one has higher variance. Okay, I think. Okay, and what you're doing is you're measuring essentially that the distance between here and the middle is some measure of the variance of the points. So you're using an extra component because these two in the first one, these lines are useless. It's just the length here. Okay, or you could easily do it this way too if you wanted to. But so you just pick an orientation, and the notch is intended to indicate something about the spread.
I mean, it's like box plot, it's median, right? So it's like this person is down here, so you part here, right? So
yeah, but you're encoding the spread, but you got the interquartile range. That's why it's not particular.
You would need means.
No. You can do whatever you want. It's kind of an art. It's not widely used because nobody understands.
What's the benefit was putting just the knots, like actual knots, and put an average and standard deviation.
So, what's the benefit? We'll come back to that. Okay. Well, actually, here, let me just show you this. No. Oh, I will. Okay, well, let's do it this way. Which do you prefer? This or somewhere, just getting there. Come on. Or this? Why? Okay, let me tell you what this is. This is one of my challenges for you. I'm giving the answer away, so that's fine. Okay, so this is actually baseball salaries, team salaries. Okay, you take all the individuals who played for that team and you accumulate their salaries this is 1985 to 2010. There's a lot of data here, by the way. Okay, there's a lot of baseball players that were playing many years here. Okay, 25 years. What are the two colors here? Good. Okay. So you got two leagues. Okay. And now you're sort of saying, okay, there's one team that was paid way more than anyone else. Any guesses? I don't know, but it's a pretty safe bet. Okay. So, okay. And then there's this. Probably the 8. Okay, this is a long time ago, but yes. Okay, and then so you're sort of seeing this, and then and so this is a box whisker plot. So you're sort of seeing the 75th and the 25th. You're seeing the median. We're adding the median in. Okay, so you're actually getting the spread here. That's what the notch is getting. The median doesn't tell you how skewed it is. So if you don't show the median here, you're seeing the skew. Okay, so that's fine. But you're not seeing any individual observations. Whereas when we go down to here. Come on. Oh, I know we'll go flying by it in a second if we're not careful. Now we're getting down to this. Which do you prefer? Notice, by the way, we're jittering these. Okay, there's too much overplotting, but because the years are, because this isn't continuous, we can actually we can faithfully say this is still 1985, even though they're not aligned. So which do you prefer?
Personally, I prefer the box and whisker because I just love seeing distributions vertically. Whereas I think this is a distribution. You can see the individual observations, overlap. I like to see what the full tiles are.
So we could add those too as well. You know, it's nice to see the individual data. It's nice. We don't need to. But what are the red dots? And you could do this with the box whiskers plot, but because they were filled in that particular case, they wouldn't show up as much. But you can make the box whiskers dots. These are the people who won the World Series. Okay, so is there a relationship between? Can you buy the World Series? Okay, okay, and Yankees. Okay. Yeah, so you can put these points on. We're using color to actually identify a winner. Okay, to separate these out. There's no doubt about it. So we like so you know, I think I drew it last week. You know, you can draw a box plot, but you can also put the points on the box plot if you want, so you still see. There's an awful lot of overload if they're done well. And this is where the design comes in. If you actually get the right sort of effects, where you have light gray or whatever it is, or dash lines, where you call out the plot, but it doesn't dominate the box whiskers, or that you make that dominant and then you put the points in gray, so people who do want to look things up, it works. This is good. I mean, this takes a lot of time and experimentation, and again, especially for the different media that you're using, as to does it work on this screen and that color. These are important things, but again, it's a lot of composition. But yes, you can do. You've got choices. These are different plots, and it's not just a question of which one you like more. It's thank you, because I like to see the distribution as opposed to I like that one. It's kind of makes me feel warmer and fuzzier. Okay, which is perfectly reasonable thing to go for, but then you've got no chance of ever actually appealing to more than 10 people because everyone's different. Whereas at least this one we have some objective criteria. Yeah.
Duncan, how do you feel about the violin?
I said that last week. I'm not wild about them because we have these violin plots, you know. So what are they? I mean, I think I did this quickly near the end. I was trying to say that I think my belief, I'm pretty certain they came from a misconception, that they came from a perfectly. I think of this as an evolutionary tree where it goes over here. Okay, and things evolved, and then they branched off at one point, and then so we branched off and did something, and then the violin plots came out of this. But we should have been going down here. This is fixing a problem. So this bit fixes a problem from here, but it's the wrong thing to fix. And the reason is, I mean, so the violin plots look like this, okay? And so you sort of see, okay, this one's like this, you know, whatever, and they're symmetric. So first of all, the symmetry is just using an awful lot of wasted space. There's an ordering effect that you have, so that the further apart they are, you can't compare. And this is to me a problem. Okay. But so this is redundant data. I mean, if you think about Tuffy introduces, you know, the data to ink ratio, which is kind of goofy, but in some regards, but it's not a bad thing. It should be high, more data per ink, so you don't have chart junk and stuff. Well, you've already divided in half, because you just got the same information twice. And then the ordering is critically important. But so what I was arguing is I'll keep it this way. What if I just take away these? That's fine. Now there's less things to actually interrupt my vision. Okay, so I can now compare this with this. And then what if I just move this? Okay, so I'll move this one because it's smaller. Okay, so now I move it and I sort of see this. Okay, now I can compare this with this. I'm probably going to flip this around because I might as well. Okay, so now I sort of get to see this. And now I get to see whatever it was, the wobbly bits. Okay, so I get to see these sort of things, and and if I had another pen, I can add in more. Okay, they all integrate to one, so one has to be higher than the other, and then lower than the other at another spot. But this grows. Okay, whereas I can't grow this one out. I certainly can't compare them, but I can compare these much more readily. Okay, so that's why I don't particularly think they're useful. They grew, in my opinion, out of this was the box plot, and Tukey, literally in Bell Labs near my old office, you know, used to draw these things with a ruler, you know, a piece of paper, a ruler, and a pencil. Okay, and you can do this. You calculate 5 numbers and you draw these things. Okay. Then we got computers, and then people said, let's go to density plots. And that's this thing. But it's like, yeah, but we didn't need to do this. We could have just gone to density plots straight away. And this, because this is over here, here we have histograms. So we went to histograms, and you go like, well, you can't put histograms on top of each other on the same plot. The box plot solved that problem. But then we got down to, hey, you can do densities. Then this became redundant. That's my theory. Okay, so I don't particularly love them because of that's why. And again, I think thinking about why is more important than you know, you still may end up in the same result. Let's take a 5-minute break, okay? Yeah, but otherwise we can just talk about some of these things. Again, it's always kind of boring in some regards because either we can't solve this problem or it's obvious how we solve this problem. But again, it's useful to think about. And I can't emphasize enough on the other reason why it's either boring or it's obvious or too complicated, as well as I haven't given you the data. It depends on the data. But I'm intentionally not giving you the data. I will if you want. I have rental data from all sorts of, for you, if you want to rent an apartment or a house, I have lots of it. Okay, and we got about 5,000 observations in my current pull from different things. What we get all sorts of information. We get the price. You get the square footage of the unit, house, or we actually also know whether it's an apartment, whether it's a flat, an apartment, a house, a cottage, a condo, or whatever. I didn't include that. The list goes on. Okay, and then we got the number of bedrooms, the number of bathrooms, the neighborhood that you're in, so essentially some aspect of geography. We actually have the GPS coordinates. Sometimes they're wrong, and so it's useful to plot them and go, that's not where you are, you can't be there. Okay, and then you got whether it's parking on street or off street. Okay, we got laundry in the building or not in the building, or no laundry whatsoever, or whatever it is. You were about to say? No? So how do you visualize this? I got 5,000 observations. How are you going to visualize it? Again, this is boring. I'm going to give you a one problem which I don't know how to solve. Okay, so if you want to go straight to okay, here it is. We can do that, but let's be. I mean, in the sense that it's seriously hard to actually represent well. You really want to do that one? How do you do this one first? Because we'll get there. We'll get there. I mean,
is it interactive?
You can make it interactive. I mean, but again, we got a medium problem. So yeah, and Jane and I will talk about how to make plots interactively. So it's not very hard to make interactive plots, but you still got to choose. You know, I'd say you've still got to actually compose a static plot before you can make it interactive. And good question. You see, that's again. I actually want to know. Yeah. What am I trying to do here? Yeah. No, this is the thing. I gave you a plot. When I said this, let's plot them. It's obvious what you can. There's so little to plot. Once you get here, you got to choose what the heck are you trying to do here. What's your message? No, I'm pulling this data from. I pull it up. What do I want to know? I want to how. Why? Why do I want to pull this data? There's different reasons why do I want to pull this data? I pull data about real estate because I want to know whether is my house going up or down. Do I want to buy another house for rental data? You know, what do I want to actually do? Am I paying too much for where I'm currently renting? Okay, so what's the norm? Sometimes, so I'm going to do exploratory data analysis on this, and other times I want to say, okay, should I rent this house? Is this way too much, or how do I bargain to actually? Is it rude if I say, hey, take $500 off, or is it because it's already a bargain? So I kind of need to know what the norms are here and what's a real good find. Okay. Yep.
So since some of these things are somewhat endogenous, like square foot, number of bedrooms, bathrooms, I would probably start off with an academic audience, or at least for myself, with correlation matrix plot, just to show the correlation between each one of these things with each other and with the variable.
Correlation plot. What do you mean by correlation plot?
A matrix plot, so you would just get the bivariate relationship between each one of these things, and you get a series of those.
So yeah. So okay. So this is so that's okay. So you're saying that there's panels here.
Right.
Okay. So I traditionally call these a draftsman's plot. Is what people have called in the past. Doesn't matter what the label is, but the one really wonderful thing about these is every field has a different name for the same plot, and that's why we have so many. And they say they all end up being scatter plots anyway, so it doesn't matter. So yeah, you can do this. Of course, this gets very small very quickly with the large number of variables. And of course, this ain't going to work out very well for Yeah, because these, so then it just falls over. You know, sometimes the software will just do goofy things. And what do you put in here? So this is variable 1, variable 2, variable. This is variable 1. So what do we put in here?
Usually that's just left diagonal would be left blank.
Yeah, or you could put in histograms or density plots and all that sort of stuff. By the way, sorry, just want to go back. I forgot to mention this. We were talking about violin plots and we were talking about density plots and comparing them, and we basically said this is better. It grows. You can sort of see the thing. It can get too much because there's too many plots, too many curves. But they don't hide each other because you're drawing the actual curve, not the area for no good reason with no good reason for covering it in. Okay, so you're doing this. I think what's the problem? Okay. Okay, I'm gonna. Okay, we'll do that. They have to integrate to 1. Okay, which one has the biggest mean?
Turns off.
Yeah, you know, I can draw the. They have to integrate to 1, so that's fine. The mean here is, you can kind of tell the mean is the middle of where it balances, and this one's slightly skewed, so it's a little bit tricky. Okay, we don't do very well here. This one's higher here. First of all, we tend to actually look at gaps this way, and not actually just vertically. So this can be very easily misinterpreted. Okay, but this one, because they integrate to 1, this one is higher, therefore it has to be lower, and the area between here and here has to match the area here and here because they integrate to 1. This is good. This is hard. This is hard to actually visualize. We can compare them and we can say they're similar. Okay, but when they're different, it's hard to characterize how different they are because, it's a little bit lower here, it's a bit higher there, or whatever it is, but what does that mean in terms of distributions? What is a better way to compare two densities?
I don't have an answer to that, but I want to get your feeling on reference line, because that hasn't come up a couple times.
Reference lines? You mean like where?
If you were to just say, yeah, exactly, vertical line at each X value for each distribution mean.
It came up last week where I think I showed a plot where there was so many reference lines you couldn't see anything. I was like, okay, I'm sure there's some data in there, but I don't know. So, you know, reference lines reference lines are very good when they actually refer to things and draw your attention to them, when they're useful and then when they're subtle, when they don't dominate. Again, it's just like less like writing, whatever it is, when they support your message. But if they're just, if it's just, oh, I better put a grid, I don't care, I'm putting that, they don't really help. Here they don't really help much because what am I drawing my attention to? I can draw the attention to this point, and I could draw an arrow here that says this is where it's larger or whatever, and I can annotate lots of plots, and I'm a big fan of annotating if they actually help explain the plot. So it just takes a little bit more effort. So many people don't do it. But here I'm actually trying to compare the distributions, and I'm sort of thinking, how far are they off? So let me do this. I've got these guys here, and I've got this. Which two are closer together? Assuming that, and again, I'm drawing this by hand, so the areas have to match. Okay, so depending on where I am, I'll make this a little higher. Okay, which ones are closer together? We're not good at this. We just can't deal with curves very easily, because especially constrained curves. So what are we going to do? Okay. And why do we want to go do QQ plots? There's a principle here. Okay, what's a QQ plot? And who knows what a QQ plot is? Okay, not many. Good, excellent. Then we have, this is a new type of plot. It's a scatter plot. Okay, but it's called a QQ plot because it actually tells what we're actually going to put on it. And the Q here, this Q here is for quantile. And this Q here is also for quantile. Seems a little odd. Okay, but the point is we're going to actually compute the quantiles for two different things, and then we're going to plot them. And what we want to see in some regards, what we want to compare it to is, if I have, here's a distribution and here's another distribution, well, the quantiles are the same. okay? And if I have something that looks like this, and then it goes off like this, these quantiles are the same, and then they start deviating from each other. So in that case, I have these three curves now all with the same color. I would actually see a straight line for the quantiles. Okay, and then I would see a straight line the whole way, and then the other one will go off and deviate over here and go back up or whatever it is. They'll deviate from a line. Remember that plot I showed you what says we're going for linearity? We can pick up linearity really, really well. We can't pick up curves. Okay, so we've tried to map something so that to say that they're the same means we just have to detect a line. So all we do is we actually compute the quantiles. We compute the quantiles for this brown one. How many quantiles? Well, there's an infinite number of them. I only have n observations, so I can compute n quantiles. Okay, and then I do this for I do it for the other for each of these three densities. Okay, and then I just plot the quantiles. Okay, and I have a scatter plot. So I have, okay, and then I can. What I might do is I might actually say, here's the quantiles for this is number 1. And this is number 2, and then this is number 3. So I might plot the quantiles for number 2 and number 3 against the quantiles for number 1. Makes sense? And if I want to, I can actually compare this. For those of you who aren't familiar with QQ plots, if I want to say, here's my density, is that normal? Okay, I just compute the quantiles for the normal density against these ones, the empiricals, and I compare them. So I can compare 2 densities or 3 densities or 4 densities, okay, or I can compare 1 to a theoretical density. Okay, I can compute the quantiles in different ways. Does this make sense? This is a very, very, not only can I see lines and deviations from lines, I can compare them and say, oh, that's much closer to a line. How do I compare 2 things to, which one is closer? Suppose I actually have a plot that looks like this. Okay, and I sort of, quantile plots often look like this. Okay, and you get the straight line in the middle, but it's the tails that kill you. Okay, and then we don't really care too much because they're kind of weird. Okay, but then we have another one that looks like this. Okay, and we get that, and then we have a third one. And you get this sort of thing. Okay, which 2 are closer together?
They're all identical.
I know, they're very, very close. So how are you going to pull them apart? First of all, you can say they're all the same. Just for purposes, for our purposes, they're the same. But how do you actually fix? I said you got to a line, but now somebody says, well, which one is actually, how much closer is this than the other one? How do you do it? Very simple. That's not. You have a line, so we're doing this visually, but instead of doing it visually, now we can actually go back to actually computing the correlation. Which one's got the highest correlation? Which pair has the highest correlation of quantiles? So we can actually measure how close they are together through correlations. And that's what you're doing visually, but now it's like back to the t-test. You're kind of just doing this visually, and if you care, you can say, hey, these 2 are almost identical because of the correlation, because that you've mapped it into this linear space. So how are we going to plot these? I mean, seriously, how many dimensions can you get here? How many dimensions can you get onto a scatter plot? As many as you want. Because the only trick we're going to use here is, you can get how many dimensions? You got your scatter plot. That's X. This is Y. Okay, so you got a point here. Okay, what else are we going to do? How would we get the number of bedrooms in here? So this is going to be square foot. And we may not care about square foot because it may be proportional to number of bedrooms. Maybe not, probably not, but it may be close enough where these are proxy variables for our purposes or not. So this is price. What else are we going to write? So how do you get the number of bedrooms in there? Size. So size. So basically this is 1 bedroom. This is 2 bedrooms. This is 3 bedrooms. Okay. Yeah. Perfectly happy to do this, but this is area, and we're not good at comparing these things. And bedrooms are actually they're not like population or something like that. These are like 1, 2, 3, 4. Okay. So So somebody else said what? We can definitely do this. This is good. Shape? What sort of shape? Triangle, square, okay, circle. Okay, this is good. Okay, what's another shape that I might use? Pentagon, okay. Here's the shape I'm going to use. Here's the one here's an unusual shape. It avoids lookup, as long as you label them correctly. You don't pick 4 to mean 1. Okay, but I mean, why not actually just put the character down here and actually say, look, this is fine. Now you may end up with a whole other problems, but if and this is why I told you there's 5,000 of these. So if there's overplotting, but maybe we don't care too much. Why did you do this? I mean, so I think this is simpler than this. Yes, it's not as pretty. Nobody likes to. I mean, these are just easier on the eyes to actually, and I think these are actually easier than these. Okay, but there's a whole legend that you have to look up. So this is a cognitive overload to actually, you have to memorize the legend and then go back. Yeah.
But if you just take the triangle is 3 and square is 4, and pentagon is 5, then you don't have to
yeah, no, so good. I mean, you can actually use the shape to count. Absolutely. There's no doubt about it. You could do that. Absolutely. But why didn't you use color? Who knew people actually listen to me? No, the color is great. We use color all the time. No, nobody says color's bad. Nobody says color's bad at all. And let me just quickly just do this thing. This or this. One's prettier, but one's also much more informative. Which is which? Okay, good. So there was no trade-off here, which is really nice. I mean, we actually get the right colors to actually indicate what the heck the parts are. There's absolutely no difference between these, except there's a whole heck of a lot of information. So color is great. I mean, you know, if you had chosen to actually make the sea blue, green, probably a bad choice. But this is like the, you know, like having the axis go down the wrong direction is probably not so good. So no, color is absolutely great. It's just, and again, going back to this stuff here, this is what's always so disappointing about stuff. This is best. This doesn't mean this is bad. And it doesn't mean this is bad. It just merely means that you're not going to be able to decode as well. So you probably don't want to be using this sort of thing when engineers are, you know, air traffic controllers are making important decisions and they're going like, well, who would have known that was twice as close as I thought, you know? But we have constraints. We have to use these things. You got to know that you're using them and that you're not going to be able to decode as well. So no, I don't mean to say that color is bad or stacked bar charts are bad. Well, I do, actually, I really do. If there's a better way, that's great. But no, color here could work, but again, it's categorical, so you're going to have to memorize the legend. So that's not as helpful. Okay, so we got that. Okay, so where were we going here? What else are we going to put on in here? Okay, let's make this big. Neighborhood. Oh, we need a map for that, don't we? No, not necessarily. Okay, depending. So now we got to decide what to plot, because I gave you these. Okay, so you could have a map. If you look at neighborhood map, okay, off we go. Except for that may not be the point of emphasis. This is merely just like writing a paragraph, writing an essay. What do you lead with? I mean, what's your primary point? Okay, my primary point is to compare price and square foot, or price and number of bedrooms, or whatever it is. If it was price and number of bedrooms down here, I probably end up with a histogram or a bar plot, okay, or a dot plot. Okay, so I could do it that way. I could quite happily do this and encode square foot by color if I think that that's the most important and relevant thing. So neighborhood, how am I going to get neighborhood in? So one thing to do is, how about this? Where are we? We're talking about, this is the East Bay. Okay, so, you know, we've got Oakland here, we got Berkeley here, we've got whatever we have, we got El Cerrito up here, and so forth. So we could actually have a scatter plot in all these points. Okay, we make a big map. So we have the map, now you can actually see things. And now you have a separate plot for each of these, which is kind of like faceting, okay, or panel plots. We just, these three, but now we're actually putting them on in context, so you can see, hopefully there's some continuity. But then again, we have to choose the point, the thing we're trying to emphasize. You don't necessarily know what we're trying to emphasize because you haven't looked at the data yet. This is the EDA versus, okay, here's the summary for everybody else. But this is all I'm trying to get at is that, you know, you can actually break up these things into separate panels. You want them to be close together if you're trying to compare. So if you're trying to compare across these two things, and this is, if you expect some sort of linear shift here, you probably want to encode that in a single scatter plot and decompose by laundry versus non-laundry. So you would, this panel would be for laundry, no laundry, okay? Or laundry in the unit, no laundry at all, and laundry in the complex. You might have three different categories, and you just say, okay, are they the same? And again, you have all these scatter plots here, and you have a scatter plot here, and you have a scatter plot here. You know, I like to draw lines. We were just talking about this, of drawing lines. Summarize the stupid thing, okay? And if it's not a line, it might be a smooth regression. Okay, but draw attention to what the feature you're actually trying to see there. And now, when I'm looking at this, I can sort of see, okay, so I have a nice plot somewhere. I think in my other slides, I'll show you, where you actually can sort of see, you see a panel that looks like you got these scatter plots, you got this, you got this, you got this. And we end up with lots of these panels. And where you end up saying, and when you sort them carefully, you end up seeing this sort of thing. This is the dominant feature. Okay, and what you're going from a positive relationship to a negative relationship, and you can actually, and then if you order them, you pick this up. It's in the scatter plot, but you're actually calling attention to what you want the person to see and ordering them in a particular way. So again, it's just the ordering part. This is the baseball one. Here's another one, okay? We actually have this data. Measles vaccines. For them, against them, I don't care. Okay, well, we can, what? I do care, no, I do. I'm not getting into that, I'm not getting into that goof. I'm not going into that goofy debate about that. Well, of course we care, but there's like, I'm not going, okay, so of course we do. So what do we actually have? Let's just suppose you have each case of measles, each reported case. You have the date, the county, and the state, and so forth. Okay, the gender of the person, and so forth. There was a vaccine introduced in 1963, and again another one in 1968, I believe. Although you guys should know more about this than I do. There was an outbreak. How did this affect things, and how fast? So there's a whole rate of vaccination to deal with. How would you plot this?
Cases over time.
Cases over. So what's that mean? And again, there's just lots of different choices. The trouble with plotting is there's no wrong answer. There's, because even that red plot that I showed you, that was correct. It was just highly misleading, but it's not wrong. Okay, it's darn close to wrong, but it's in. So what would you plot?
Number of cases.
So this is the number of cases.
Yeah, high, and then over time.
Over time.
And then you can annotate when the vaccine was introduced.
Okay, and we put in 1963 or whatever it is, and we annotate that fine. So what happened to the state? Whoa! I could facet it. I mean, I could do. What you're basically going to do here. We're hoping this looks like this. Okay, so we want that to happen. Okay, and it turns out that it probably turns out to be something like this because people weren't being vaccinated at the same rate, but eventually the uptake kicks in. We'll see this. We could actually do it by. We could do it by. We could do it by state. Okay, so this would be another state. Okay, we could do that now. We compare. There's 50 states.
Then the population of the state would be percentage.
Maybe. So do we want to actually? So this is an issue. I didn't tell you we had population. So yeah, well, that's fine. No, it was ... So yeah. So do you want to normalize? Okay, this is important. What else?
I think the idea you gave there, so we put it on the map.
On the map. We could, but now we're looking around all over the place. We're doing gymnastics to actually figure out. And remember, what's actually happening is, so just like what we said about the number of bathrooms or whatever it is, whether it's got laundry or not, you actually have to say, what's the legend? Lock it in your brain, and then go around and carry that in your mind the entire time, and actually and do this lookup in your brain. If you can't memorize the legend, you got to look it up in the legend each time, and that's so it takes time to start familiarizing yourself.
Can we animate it?
No. I'm not letting you animate it yet. Yep. No, you could do that. You could animate it. What would you animate?
I'll probably put them all on that.
And then just change over time.
Have a density on the map over time.
Yep. So you could do that.
You said something about like trying to see how.
No, I was just I'm trying to see the opposite. I'm trying to see the outbreak disappearing. but yeah, you can do it. Again, there's nothing wrong. No, of course you can animate, and that would be great, except for that darn epidemiological journal that is printed doesn't work this way, and it's still amazing, at least in statistics, where there was it was a couple of years ago. I shouldn't be that. But they just figured out. They actually had a little article in one of the Journal of Computational and Graphical Statistics saying, "Hey, we can actually put in live plots." It's like, of course we can. We've been able to do it for years, but but it, not in every version of PDF. And you got this as a little odd. Okay.
If you want to go with the one suggested, so having 50 on top of each other.
Yeah.
And then I would have used a kind of coloring. So say like if I actually see this pattern that is from like east is more effective than west or west is weak, so I would use a spectrum for like the location of the state. So it's kind of I color it to say.
So you could, but you got two dimensions.
No. I mean, so you have one curve for like Washington.
Yep.
California, and then what you can assign a color to this California.
Yep.
And then like you can, if your question is like from east to west, you observe actually it's quicker or west to east,
or north to south.
Yeah.
Or diagonally. Okay. Oh,
I think
yeah.
because then you can convey that you see like these the states that are on the east are more effective.
Sure. So we could do this. This is a plot.
Yeah.
I'm gonna. It's just one plot. I'm just saying it's a different type of plot. It's not a scatter plot, really. It kind of is actually. Okay, but it's got more to it. It's kind of it's a calendar plot. It's kind of interesting to see that this is what some people have used. Does this make sense to you? So you sort of see now you actually have a lot of information here. You've held the state around. Okay, it's not clear that this approach isn't better because you've actually got it over a year and you've got the same information. You possibly have easier information in this. It does make the case pretty clearly what's going on. Okay, you also see these guys, this guy, which is interesting. It's Iowa. Okay, so and these different. I'm not sure which is more effective. This than that. This one you can't tell which state had the most in 1962. So here's 1962. Whereas over here, I can actually just, I look at the topmost in 1962, assuming there's not too much. So this is kind of weird. It's kind of nice. It brings you in. It doesn't.
Yeah, I think it just depends on your message. Like if you want to convey the importance of the vaccination campaign, I'm more drawn to this one because it's a stark contrast, and then if the kind of effect is intuitive for people, hot versus cold. Cold is good in terms of their health rate.
Yep. I mean, if you're just trying to show the cutoff point, I mean, I drew the cutoff point very. We would have seen it over on that plot too, especially if you don't put the 50 states in.
You also want to know that this message, but also your audience. I see the one that word, if I really care about my state.
Then I can.
Yeah, that's kind of nice, right? Then you look at California and you know you're moving on, there's like one or two.
With that one, you're saying? Or this one?
Sorry, the one on the screen.
Oh, not the board. That's the board. I was going to say this one. It's kind of hard to tell though. I mean, this is not. Now we see if you are looking for California, your color is not working for you here. But remember the color. What I said about the cues. You're now off on the color. We're not using lengths. If you're interested in your own, if you're in your own state. So this is actually hard work.
That one would be really nice if it was interactive. Click on California and it would show you gray out all the other ones.
It would be, wouldn't it? And we'll do that in a couple of weeks because it's the most obvious thing to do is just like to because you're interested in California, but somebody else is interested in something else. So we can't have 50 of those plots, but you are changing context, and that's really obvious. Yeah.
So with this example in the last couple that you pointed out how important color can be, how useful color can be. Do you know of any resources off the top of your head, colorblind, where we can?
I do. There's a lot of stuff. Yeah. So one of the important things is if you're choosing colors, there's a woman called Cindy Brewer who actually has this thing called Color Brewer. Okay, with her name, but it's good. Which is actually she's done a lot of work. She's a geographer, but also a sort of cognitive scientist as well. And she has palettes that you can choose, and they divide them into 3 different types of qualitative and quantitative, and there are ones you can choose, and she has an interactive website. They do a lot because she's a geographer. They do a lot of maps, but you can actually go in and choose the right number of categories that you want. With that, it restricts it down to different choices, and then you can actually see them interactively. And then there's a bit of color blindness. One of the nice things she has in her webpage is that you can change the medium. Or more to the point, it says this will not work on a projector. This will definitely not work on this medium, or this is compatible with this. And then there's color blindness. And then there are these websites which everyone should do it. Nobody does, but me too. Is that you take your plot and you say, now show me this image through the lens of different color blindness, and you go, oh, that doesn't work. Or that does work, it's fine. Because color blindness isn't, as I was just looking at, as many people are adamant, it's like, it doesn't mean you don't see color, you just don't see the same range. So you can still use red and green, even if those people are red and green colorblind. You just have to get the right saturations in there so that you can actually pick up on them. So yeah, there's thank God there's a lot of tools now. Because it used to be, it was like, yeah, who cares?
I'm not colorblind, there's very little difference between 1,000 observations there and 4,000, or maybe I am colorblind.
This has all been about, we just wanted to tell you that you were colorblind. No, I mean, this is a real problem, which is it's like the density estimation that you do. You get to choose the rate at which these change. And this can really affect how people see. I can't see. I mean, here, what the hell is going on over here? By the way, there's a fun thing here. There's almost no measles here, which is weird because Georgia has almost none here. These are actually, I think I can tell the difference. These are missing, These are actually structurally zero or very close to zero, which is kind of nice. You get to see this in some.
What's the wise? Because it doesn't seem like it's everything. It's got one row. It's more rows.
More rows.
Yeah.
There are more rows than which?
States.
Oh, I don't know. I would suspect. I suspect that there's not 50 states there. So I suspect what's happening, like with every piece of software, go like, yeah, I can't fit it in there. You'll just put every second state. And this is the size issue. We run into this all the time, as we'd like to label, but we can't. So then you put them on over here. So now you can alternate, which is a hard look. But then you're squeezing the size here. And these are not very big. The bigger you make these squares, the easier you can interpret the color. Yeah. So, it's an odd choice here to be using color when we had length over there. But it works.
If you just did it in grayscale.
Would it work? Probably. And remember, there is this nice phrase, and get it right in black and white. Just because it's universal. If when you're actually on a printed page, you have it. And again, life has changed since I was born, and everything was black and white, and color was, oh my God, I'm not that old. You're all going, yeah.
Sorry, what's the name of this plot? I want to implement it. How can I do
I'm not sure what the name of it is. It's kind of a calendar plot or a timeline plot, but a calendar plot. I'm not sure. The trouble is they all have these goofy names. It's a heat map, but then people actually do them with calendars. Okay, you actually have, when you look at your Google Calendar, you have these cells, so they use them for that purpose too. But yeah, it's a heat map is all it is. You're color coding a value in here, which is the 3 dimensions. It's the count here, and you've got these categorical variables.
So something else I found really interesting on this one, and it's actually come back and help me when I was making some figures. If you look, we talked about perception, right? 1K to 4K is hard, but 0 to 1 is a little bit easier. So there are all kinds of things depending on your message, your audience, kind of where you have that scale going, you can help orient people to pay attention, or just lie if you're.
So you get to choose these colors. This is what I was saying about choosing this palette. Is you just get to say what the increments are, and these are nonlinear. Okay, this is the problem in color, but they may be linear in value, and we don't have that connection in color. That's why. Remember what I was saying about colors? Remember that plot where all the electric shock plot, where we don't pick up color as well, the change in color. So you can try to adjust for that and try to linearize it in a particular way. Okay, here is. So this is an interesting plot. This one. This is very similar to a scatter plot. There's nothing new here except for it's a different composition. Okay, you are actually doing something slightly different. So it's worthwhile going out and seeing what works, what doesn't work. Let me just. Okay, here is a set of data that I actually have, and I will give it to you if you want. Okay, but before you do this. Okay, before you even look at the data, I want you to think about this. This is an experiment that was done over in Germany in Mannheim, okay? And here it is. It's a building like this. Just think about a building here. We have routers. We have wireless routers in various places around here. So what they're trying to do in this experiment is they're trying to be able to figure out where you are based on your signal, your cell phone or your laptop signal to the routers that are fixed in fixed places. We know where the routers are. We get your signal. We can figure out where you are. Okay? So it's just geolocation. It's a very useful thing. It's better than GIS because it's much higher precision inside. So it's potentially useful in emergencies, in earthquakes, except for the routers aren't there. It's a bit of a problem. But when people have actually used this for things like finding things in hospitals where there's a very expensive machine. Where is it? Somebody's got it. Let's just find it really fast, as opposed to calling and saying, hey, who's got the machine? We just know where it is because it's broadcasting. So you have these 6 routers. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 5, 6, and where's 4? I think it is down here. Good. Okay, so you have them in there in slightly odd spots. But the interesting thing about this experiment is the following. They know this. Okay, first of all, you can argue. I used to work in Bell Labs where they did a lot of networking and communications. The further you are away, the weaker your signal. You all know that. What's the relationship between distance? Whatever R squared. Okay, so it depends on whether there's a wall in between, and is it exactly right, and there's a whole lot of other things, and of course it's not R squared, it gets truncated. You have no signal essentially at certain places, so there's walls. What else does it depend on? Wall. There's a wall between you, that's fine. What else could be between you? My cell phone. I'm walking around with my cell phone. What else? There's the make of the router. We actually know this. We actually have the MAC addresses for those. We know this. There's one other thing that actually... Why does that matter? It's not so much whether it's out or about. That does matter a tiny bit. What's much more important is if the router's here behind me and I'm standing right in the way, that's a problem. Okay? The human body being made of water and all that sort of stuff apparently does kind of... Well, that was their conjecture. Okay, so what do? All of these circles represent some poor grad student, okay, was given a device, okay, and said, stand here, okay, so they walked in and they stood there, and they held this device and they got signals. This is odd, it's actually gone backwards. They're detecting the router's signals. And anything else that's in the, anything else that's wandering around the building. So there's other people with laptops and cell phones, and we get them as well. But don't worry, let's ignore the extraneous ones. Let's suppose they've cleared out the building and everything's fine. So they stand there and they take a signal that they say, okay. So they're standing here and they get, a very high signal from 1, reasonable signal from 2, something from 3, 4, nothing from 5 because it's too far away. Okay, now when they move over to here, they're going to actually get something from everybody and so forth. But not only that, they stand there. There's no point. We're statisticians. Okay, we like this. So they stand there and they take measurements, and they take at least 110 of them. Okay, so you got repeated measurements, so that there's any fluctuation and all that sort of stuff. And then what do? They turn around very slightly, 1 degree, and they do it again, 110 or so. Okay, do it again, 360 degrees, okay? So you got 110 per degree-ish, and we actually have the degree, okay? So not just like we actually record it. It's not 1 degree, it's 0.99 of a degree, and then they're wobbling around, okay? So that's fine. So we have 110 observations for 360 degrees. And then they move here, and there's 166 points. And at each of those, you have a measurement to 6 routers. It may be missing because you may not have the signal. Let's visualize that. I told you this was going to get hard because this is a serious amount of data. But the trouble is, for me, I want to know is the relationship 1 over R squared? Is that going to be good enough? So this is EDA. How do I model this? Okay, so this is not just summarizing it.
So this makes it easier.
No. Yes.
So you just put on 1, you plot that 1, and then you have another 2, 3.
Maybe that'll work.
And then if we want to do for 1, just one of them, I use those arrows we discussed.
So we could do that, yeah. So let's do this, and let's see how far we can go. So yeah, remember those windrows plots? You really do have these angles now, and you do want to know that when they start off, the person's there, that when they go all the way around and they're back to here, you want to compare those two. They should be the same. So okay, so we have a point here. There's my circle here, let's say, and we're only doing it for 1 router. Is that what you wanted, or 1 point?
1 router.
1 router or 1. Average 110? No, you see, I need to know about the variability. Remember, I'm doing EDA here. Are they skewed? Is there a time trend? Am I actually losing signal as I stand there? Or am I gaining signal? These are maybe different questions that we don't do in the same plot, by the way. This is because you may be asking this plot to do a little too much. Okay? So, anyone? Take out a piece of paper. I'm curious. And you can work together, by the way.
Kelly.
How to get, the beauty of having no data is you can do anything you want. This is unconstraining, because this is one of the ones where I just can't figure out how to compose it. Yeah, you don't have to work on a stamp. Yeah, making it even harder. It all has to. It all.
But you don't have
See, now your log problem is much easier.
The measurements have an order. You always have you do 110 each.
About 110. So another thing you'd like to know to some extent, you may or may not want to know, is how many observations do you have? Because if you got 300 observations at the same point, that may or may not matter, but so we may want to include that as n.
That depends, because if you're going to compare, let's say, over time,
yeah,
you are interested. If you have 300 observations in one position and only 100 in the other position, you are losing time idea.
Your
first 100 can be compared, but the other 200 cannot be compared with your position.
Maybe it depends. I mean, now, so you're introducing time series. Do you want to compare across time, all the points at the same time?
I'm giving you an order for, if you want to represent all the points, give them an order. So
yep,
we always have the same order for each position, for each group.
Yep.
Because that's the way you can compare it, and you can have like information. But I imagine, let's say that they turn and they always take 100 measurements, so 100.
Pretty much.
They are all done. It's synchronized.
Yeah, so they're at different times. Yeah, at each point and at each angle, there's only one person wandering around with one device. So but you want to know. I mean, one of the questions I actually have, and it turns out to be, you can look at the times they were taken, and they were taken in 2 different sessions. Now that always worries me, because was it the same person doing it?
Yeah.
Because now we actually may have. Yeah, or maybe there's this one very large person and one tiny skinny person who doesn't block the thing, or that one person is just really inattentive to detail. So I kind of want to say that one person is going, they told me to take at least 110 measurements, but I'm going to take 200. And the other person says, they told me to take 110. I'll get it down to 90. I'll be out of here. I'll be out of here before the, and then the quality of the data. So we're going to look at lots of different things, but it's still spatial. So like the number of observations is one thing we may want to plot.
Yeah.
But there's still per angle, per location. For God's sake, this is hard. So I'm curious as to how you can create it.
So the question you want to answer is, if you are a certain location, random people in this group, what's the signal you pick up? So you assume that the direction is pretty random,
Yeah.
The probability of these certain location, like directions,
Well,
is it clear?
yes, but so I mean, so ultimately, that's what we want to do. That's why I'm asking you this is exploratory data analysis we're doing, and we can look at lots and lots of plots. There's also another thing is like, how do I summarize this? But for other people, but that's another. Ultimately, we don't care. Nobody sees the data anymore. It's just, can we predict? And then, one way to do this is you don't know the orientation of the person you're looking for. You only have the 6 signal strengths. So the question is, what you want to do is you may want to be able to look and sort of say,
but maybe you don't care about orientation. You care that no matter which orientation, there is one router that will catch the person.
or actually, you need at least one router, but you actually, so let's suppose these two, you might be able to say that if I get a signal strength of -70 and -20 for here, with this orientation is different. I'm closer to that. I'm more similar to that than with a different orientation and 2 different signals. So what you're looking for is the best match, and saying that's who I'm going. That's where I think you are, based on. So what you've got a whole lot of data training. This is really training data now, and you're saying. So one way of doing this is K nearest neighbors. You say, who do I look closest to? And now you're taking in their orientation, and you're sort of saying, including that orientation information, I think you're there. But it's going to be close, because it might be that you're in a different place with a different orientation, and you look very similar. So I don't know. Yep.
Are you measuring overall signal strength, or are you getting a different signal strength per router?
I'm getting the signal strength for each of the 6 routers.
Okay.
Yep. So I got 6 numbers for each of the 110 observations for each of the angles. Yeah. Yeah. It's a lot of numbers. There's a lot of numbers. Yeah. Finished? Got it? I want to see this picture. I want somebody to come up with a beautiful plot. It's tricky. What? See, what I want to do, so that you can have multiple plots, but it's nice to have one good thing. I want to compare lots of things. I do actually want to know, how many observations were there at each point and at each angle. Was it reasonably uniform? Or should I go back and actually say to the grad students, you did a lousy job. You're all over the place. I might. That's one thing, but then I want, so I've got this. I mean, I can count the number of points at an angle and a location. Okay, and then I can just, plot them if you want, but I can't be. But now I go like, that's weird. Okay, that's even better here. They missed this spot, or they only took one observation here, or something like that. Okay, but I can look at this and I can color code. How do I get the angle and the location in here? And clearly, I can put it on the map. I could put it on the map, and then I'd have the location, but I don't have the angle. So, I could, if I wanted to, I could put a density plot here. Okay, or I could just put a dot plot for the angle. Just here's the angle, here's the counts. I see they're uniform, but I need a huge screen to get to all those guys. So is there a more compact way? You're cheating. You're adding the dimension. No, I'm in EDA mode here. But it could be. Potentially, yeah. I mean, yes, this is why it's so hard, because we're going to use the same. We can use the same plots in both, but the constraints are different. So yeah, absolutely. But you can make it interactive. But making it interactive as opposed to animated requires somebody to go around and pick up a lot of information. They have to click on each thing. So you could quite happily see. I could draw a density plot here, if you will, or angle, and then the counts. Okay. But there's too many of them, so I have to hide them. So you're telling me that I can go in and click on each one and pull it up, and then I'll just mouse over. I won't even. I'll save you the click. I'll save you the energy. You know, but then I can't see them. I have to memorize them and go like, oh, I remember there was one like that before. Let me go back. So I can't see all the data to actually make. Yeah, there's no problem like this, like that, or that one or two of them, or maybe there's a spatial pattern here that says they started here and they were very attentive, and then they got generally less attentive, you know, and it goes in this direction. We need to account for that. I need to see that all in one go to get that, but it's an aggregate. But I don't want to aggregate. It's EDA. I want to see the individual things. I can't. So.
Not the strength versus so I want to model, right? So I want to know how things is
yeah. Okay, but we're
functional system, right? I want to look at the chair, not the model.
Yeah.
But so this there are angles and attention, like time, whatever you want to talk about.
And there's, but one of the really important points is there's walls, because it's not a function of distance. It's a function of layout, you know, which is, so you'd like to see that in a plot and say, why is that point so weird? Oh, it's because it's behind the wall. So, because we can just compute the distance. Oh, but by the way, I do know where all the routers are. I can give you that extra data. So you can compute distance, but then when you get these odd points that aren't on the, and by the way, I'll give you a guess. There's an office here, there's an office here, there's an office here, there's offices here, there's a corridor here. So you can see the layout of this building. So you know the walls are all over the place. So that this is, it makes life more complicated because you have to take those into account. Or not. I mean, I think if you were to draw the plot of signal strength to distance, so now you compute, you've got all these things, you throw away all the location because it's supposed to be invariant with respect to the actual, okay, you can plot that, and if you see that it is a beautiful, they're all the same, you go, great, we're good to go. But when you don't, you're going to have to back it up and see if there's bits you can recover, and then you're going to probably have to map it onto this. Sorry, go ahead.
Yeah. Oh, I'm just thinking, I mean, like when we start talking about like disease modeling, logical modeling, you can make it really big and ugly to try and get as much of like the stochasticity or variance or whatever.
Yep.
That might not necessarily be the best model. So trying to first figure out like what variables are important versus maybe body size doesn't matter. And so actually having to display that and show it graphically isn't that important.
No.
Or like the angle, maybe that doesn't.
But before we do that, exactly what, so there's these two purposes. One is exploratory, so you have to rule these out, but you've got to take into account that there may be some interactions between these. So, and then when you've done that, sure, then like we're clearly not showing things that are completely irrelevant, like, you know, time of day, which we hope is not relevant here to when they took the measurements, maybe not. But yeah, so there's the two purposes. One is sort of evidentiary and justification. The other one is pure exploration.
So I was just, I mean, would you, I was thinking of, well, maybe just start asking your data, what is it doing, and not visually seeing the trend. If there's so many different like parameters, and like build a model that shows these are the things that are important, and then maybe visually try and.
So my argument about that is you can't build a model until you actually look at the relationship. Well, you can. People do it all the time. Is they just go like, there you go, I'll be back in an hour. You know, you know. So I want to plot them. So oftentimes we'll plot them before it's okay. Because one argument is that it's you know, the two physicists in the room, or two of the physicists in the room said, hey, it's 1 over r squared. That's now. I would beg to differ. Okay, there are more subtle versions of that, I think, that people have used in networking for this sort of stuff. Okay, which is it? Which model should I look at? But I need to actually sort of look at the data to see before I model, and that's one of the snags in my mind. So you've still got this complexity to start with. So as a statistician, I argue you do EDA. My argument is you should never be surprised what model you fit. Okay, you should see it in a plot, you fit it, and then the only purpose of the model. No, I'm being far too, but you know, it's just to parameterize what you see in the plot. So I want to see it in the first place. In which case you gotta go find out the bit. You gotta say, oh, it's a squared model, or it's a log of sine. It would be probably better. You can try that with cross validation, but I want to see it in the plot first. So it's hard. Is what I'm getting at. But yeah, but it's hard. Yep. Sorry.
Oh, no problem. So one of the things that we were trying to test here was, is there any interference of body material in terms of your signal?
Mm-hmm.
So you also have to take into account the number of bodies in your location on your line, or the ones that come around.
Where it wasn't quite done, but the idea is that they, in one case, they did this in 2 different periods. And again, I had to go find that out. I'd actually grabbed the times, looked at it and go, somebody did, one of them was during the day and one of them was during the night. So the idea is that there's no one else around here. So you can ignore that because we don't have that data. So and this is where we want the 110 observations. And we'd like them to be spread out enough so that people are walking by. So the other thing you want to find out is there's 110 observations. I mean, and you know, that's a very good point. Just from a ruling things out point of view, let's look and see how long those 110 observations took. Did they take 5 minutes? In which case, I'm not worried about this. If they took a nanosecond because the device is just going, okay, then there's, if we're getting weird, we could have massive outliers where there's, you know, a whole bunch of people walking into so you want to see that, and you want to sort of see, is that consistent? And again, it doesn't have to be done in one plot. You can quite happily say, what's the duration of the measurements? And you can plot those, you know, here's the, now instead of number of points, it's the duration, and you'd have another plot like this, but you haven't mapped it back over to here, and you haven't mapped it to the angle. And if you're sort of seeing that they seem to be getting faster as they go around. Oh, I'm just conjecturing, but these are the things I like to look at and go, there's an operator effect here, and I can pick that up, and that's why I don't believe this. It means I can't model that. I actually have to find it. So it's tricky. Unless anyone has any questions, we're just going to end like this, because we haven't solved this. You can stay here for hours and solve this. I like these ideas of and I also like interactivity. So that gives you. I also like this notion of not just interactivity, but I'll get there. So one of the things you can kind of do is you have a point here, and you have this windrows plot. You can actually have windrows plots if you draw them carefully, where you can actually have things.
But in that case, your line will be an average of the 110 signals.
I could actually have 110 there, because I could, if I wanted to, have them as a rug plot along the line. Okay, I can take this to the nth degree. Okay, I'm not saying you can see anything. I'm saying, okay, but let's just say that this line here, these are all the observations for the 110 at this angle. Okay, to router 1, and from the red one is to router 2 to router 3. Okay, I've gotten a lot of information on this plot now at this point. I've got 110 by 360 for this point, and if I make this sufficiently small, I can get them onto this. I can have another one. I can have another one here, and another one here, and another one here. And one of the nice things you can actually do is, if you have interactivity, and this is you can actually say, okay, I can see a pattern here, okay? But if you can zoom in a little bit, and this is what people do with fisheye lensing, you come across this, whereas you just move over, it magnifies. It's just like having a magnifying glass, so you can see detail, but then as you move, it disappears. So you get to see the aggregate pattern. Now, there's another thing, by the way, here that is going to be fun, okay, which is next week's workshop. Suppose I said, let's try this. Yeah, for each of these locations, you have 110 observations for each of the 6 routers. Let's just take 2 routers, okay? How the heck are you going to plot that? I mean, literally, on a computer. How are you going to make the computer do that? Because you are now in a world of your own. There's no, I wonder, does R have a function to draw these windrows plots with rug plots on top of them, okay, at each of these things for 6 different things on a map. Okay, and there's actually a nice idea. There's actually good things. If you had a plot, this is where you won't get it. I mean, so those of you who use ggplot, how are you going to get ggplot to do this? It just doesn't fit into the grammar of graphics very easily, but it does. You draw this plot. This is the polar coordinate plot, by the way. You can actually dress this up as it's just observations. What's the scale? If you put it on a scale with polar coordinates, it just works. Okay, so you can do that. And then you just plot this. Now, the only snag about it is you actually have to plot it here. So you have an X and a Y coordinate here. Well, that's just, you take this as your plotting symbol and you plot it at X, Y. And this is what the grid system does for you in R, which is it just says you can plot this independently. It has its own coordinate system. It has its own scale. And then you pick it up and then you put it into a bigger coordinate system. And now all of a sudden you get to reuse these tools by saying, I know how to draw that windrows plot, and I know how to draw a scatter plot, and I can combine the two together. Okay, very, very simply. It's not that simple, but that's conceptually where a good model where these are reusable elements that go into a bigger coordinate system works very nicely. And that's when you want to build very elaborate plots, that's what you're going to need to be able to do. But this is a tricky one. By the way, that's one plot of this. Okay, I can't remember where I have them on my computer, but I can't find them easily. So this is a book that Nolan, Dan and Berkeley and I wrote. This is a contour plot, and you actually see these. We facet these one for each of the 4 routers here, rather than all 6, and you can actually do a heat map as to what the signal strength is. That's one approach here for looking at signal strengths, but it doesn't get you into the variation of all these different things. You better believe we did, because again, the goal is different. But I mean, if I wanted to show, and what's the standard error for each of these points? Oh, for God's sake, this is seriously hard. But I haven't shown you. I haven't been able to combine on this. You know what's going on with the. You can see the walls if you wanted to, but I haven't been able to connect the routers on the same plot. These are different plots, so you're looking around. It's not so hard. There's just no winning in graphics. You have to give something up. You know, you're summarizing, but you better the only thing I've been trying to say to some extent the last 2 days, spent a long time saying it, which is just be conscious of what you're giving up. You know, you make decisions and you actually get to control this stuff just like you do when you're writing. But it's seriously hard until you get to interactivity. And then you go, it's seriously easy. You know, now we have so many more degrees of freedom, but then you can do seriously stupid things with them. But it's also a lot more challenging to actually program. So Jane and I will talk about how to make some of these very simply, and then how to actually people build, because you can do anything in interactive plots and animated interactive and dynamic plots. People have built out templates for doing all the canonical stuff, but only a few, so they only cover a small thing. So when you want to get it to do that plus a little bit more, it's helpful to know how to reuse those tools and then just extend them a little bit, which is actually not too hard. Anyway, hopefully this was kind of wacky. I kind of intentionally just wanted you to sort of start thinking about some of these things. Be very curious as to know if it was actually of any value or not, or how we make it better potentially in the future. Otherwise, I have all these other slides about color and all these other principles, which are fine, but they don't tell you how to. They just tell you what not to do, or some of the principles. If anyone draws a nice plot of this, please come and talk to me. I want to see experiment. I have all the data. I will post. I'll put the data up on the webpage. Yeah, absolutely. I have 2 sets of data, which makes it even more fun. I have training data and test data. So now you actually want to compare those 2 as well to make sure that they're the same, because there's no point in having a sample and another set that are totally different. So you have to compare these. It's like, oh. So now I can make this even harder by actually saying, now compare these 2 data sets in every single dimension. Okay. So yeah, I will post those. It's also a cute data set because it's a challenge to read in. It is not in standard form. Okay, I'll show you what I'll show you what it looks like. Okay, I'll show you what it looks like. Sorry, it's not, I think this is, hopefully it's here. Yes, this is the data. And here's a programming challenge for you. This has nothing to do with graphics. Oh, by the way, this is just to recap what I said last time. This involved reading this data in my mind involves graphics and visualization, and the reason is because you have to check if your code is correct. Okay, so you need some summary of all of these things. You notice, by the way, it said, "Do you really want to open this?" It's 48 megabytes big, so it says. Oh, it's 151,000 lines long. So there's 151,000 observations. Okay, 166 by 110, approximately. There's a fun part here. You see this? It starts off here. With some comments, giving some metadata about how it was collected, which is really, really useful. Okay, so you skip those 3 lines, and then lo and behold, just because they're annoying, they have more comments later on. Okay, way down. So okay, so that's fine. I use this just for fun. I can read this data in and arrange it into. So you look at this. This tells you the time the person was standing there. It tells you the ID of the device. This turns out to be the same the whole way through because they were only using one device. It tells you the position, their X, their Y, and if they were jumping or not. Okay, okay. You've got the 3rd degree. That's fortunately 0 the whole time. Okay, you've got the orientation, the degree, and then you stop. Okay, that's the same for every single, these are the same fields, which is describing the device. And then after this, you get a variable number of signals that you detected, which are, here's the MAC address of the router or the laptop that's floating by or the cell phone. Here's the signal, -38. The next one is, 24. You can't see this, but I can apparently. Okay, the next line is 2437000, which is the channel. There's 2 channels that you're broadcasting on, like 5 and 2 gigs or something like that. And then there's the other thing, which is what type are you? Are you a fixed device or are you mobile? Okay, but then that's repeated because I detected router 1. This is router 6. This is cell phone number 2. Okay, so what I want is this. You take each of those lines, there's a variable number of observations. I want time, degree, X, Y, okay? And then I want which router I was talking to. And then I want the okay, and I want the router ID, and I want the signal strength. So this one line will have this element here will correspond to 1 row. This element here will correspond to 1 row, and we'll repeat the time, the X, the Y, and degree for each of those. That will make my life easier if I do this. How do I unravel all of this data into a data frame that has this many rows? So I had 151,000 rows. I should end up with about 1 million. Okay, each row should expand out. I can write this in 5 lines of code. That's a challenge for you if you want to actually, okay, in R, I can do it. I can do it in 1 line of code by just combining all the commands. But you can basically do this. You can actually arrange all of these observations. You can split this out and split this. You can do it all with regular expressions. You can do it with essentially 1 regular expression. It's a magic trick. Okay, it's worth thinking about. Anyway, I will post this data. You can play with it, and if you get some good plots, I would love to see them. And if you get some bad plots, I'd still love to see them, because you have to experiment with this stuff and go like, that doesn't work. And then you volunteered to do the interactive version. Anyway, good. So hopefully we'll see you in the next couple of weeks. Have fun.
Duncan's not here yet.